Now, do remember that around a source charge, this field or region in which we experience the effect, this is called electric field. Okay, and then we can draw the electric field in terms of electric field lines. Okay, we can draw the field lines around any charge. Okay, so these are called electric field lines. We call them electric field lines. Now, what are electric field lines? So these are actually the path which test charge will follow if it is kept near to the source charge. Now suppose this is the source charge and we kept a test charge near to it, positive test charge near to it somewhere here. So what will happen, do you know? That this test charge will get repelled by it like this. Okay, and that's why we have drawn an outward arrow here. Similarly here, outward arrow. Similarly here, outward arrow. Here, outward arrow. Here, out. So around a positive charge, we can see that a test charge when kept, a positively charged test charge, of course, needless to say, it is always positive. Test charge is always positive. So when we keep it, then we observe that the electric field lines are shown like this. Now suppose instead of a positive charge, had there been a negative charge. So let this is a negative charge. Now what would have happened if had there been a negative charge, negative source charge? You can see that the electric field lines would have come towards this negative charge in such a situation. Okay, so you can see that electric field lines, they are actually coming towards the negative charge. Why? The reason being because the positively charged unit positive charge, it gets attracted towards the negative charge. Okay, so this is how you can draw the electric field in terms of electric field lines. Now there are certain properties, okay, there are certain properties of electric field lines which electric field lines are supposed to be followed. So what are these properties? Let's try to understand. The first property is that electric field lines are continuous curve. They are continuous. Okay, electric field lines are continuous curve. Now what does it mean? It means that electric field lines are, once they come out of the charge, they will form a continuous path. Okay, I said continuous means there won't be any break. Okay, there won't be any break outside the charge, they will be continuous. Having said that, do remember that they will not form a closed loop. Okay, they do not form a closed loop. Okay, these are two different things. They do not form closed loop. Now what does it mean? It means that the electric field lines inside the charge won't exist. Okay, they are continuous, means there is no break, but they do not form the closed loops, and that's why inside the charge they don't exist. Inside the charge body or inside the charge do not exist. Okay, they do not exist. So make this thing very clear. Second point which comes is, so this is first property, that they are continuous but not closed loop. Second point is, suppose that there is an electric field line like this. Okay, this is an electric field line which we have drawn. Now when we are drawing an electric field line, suppose we draw a tangent at any point of the electric field line. Suppose we draw a tangent somewhere here like this. So if we draw a tangent at this point somewhere here, at this point of the electric field line, do remember this, that tangent to the point, okay, tangent at a point of the electric field line tangent at a point of the electric field line of electric field line gives us direction of electric field at that point. Okay, it gives us direction of electric field at that point. Agreed? So this particular point, if we are saying, say this is point number 1, at this point the direction of electric field is this shown here. Suppose at this point we are finding the direction, so what we'll do, at this point we will be drawing a tangent, and this will be the direction of electric field at this point. Okay, so this is how you can actually find the directions of electric field. Okay, this is one more very interesting property. Then comes the third property, and the third property says that if there are two electric field lines, suppose these are the two electric field lines. Okay, this is one electric field line, and there is there are two electric field lines. Okay, one is this, and then another one is this. If we have two electric field lines, do remember that two electric field lines will never intersect each other. Two electric field lines will never intersect each other. They will never intersect each other. Why? So you see, why will they not intersect each other? For that, what we will do, suppose they intersect. So we can do one thing. See, here we can draw a tangent. So here I have drawn a tangent like this, and this tangent is drawn on this particular, say, number 1, and then we can draw another tangent on the other one. Okay, see this one. If we draw another tangent at this point on the other field line, this second one. Okay, so you can see that we are able to draw two tangents at the point of intersection. Okay, at the point of intersection.
Is that there is only one tangent which can pass through one point?
Yes. So if we can draw two tangents at the point of intersection, it means that there can be two directions of electric field, because we studied that if we draw a tangent at any point of the electric field, then that tangent gives us the direction of electric field. So there can be two directions of electric field at that point. Two directions of electric field at that point. Two directions of electric field at that point, and this is not possible. You can't have two directions of electric field at a point, and that's why this is not possible. Okay, so this is the third property. Then comes the fourth property. Now in the fourth property, what happens that electric field lines are always normal to the surface of the conductor. See, suppose that there is a conductor. Okay, and if you are drawing the electric field lines around this, so do remember that electric field line will always be normal to the surface at an angle of 90 degree to the surface. Okay, always normal, perpendicular to the surface at any point of the conductor. It will be always normal to the surface. Now what may be the reason behind this? Now the reason is also very interesting. Okay, do remember, if imagine that they are not normal. Okay, suppose they are not normal, so what we will do, say we have taken a particular part of the conductor and we are assuming that they are not that the electric field here is not normal. Suppose the electric field is like this at an angle. Okay, so if the electric field is like this at an angle, okay, so what will happen, there must be a component of electric field acting. So suppose that the component of electric field is acting in this direction like this, This is one component of the electric, say X component of electric field. Oh, okay. Now any charge which is present at this point, what will happen? This charge, over this charge, this component will be acting. Okay, and if this is component is acting over the charge, so this component of the electric field, this component of the electric field, okay, what it will do, this component of the electric field will produce a force, and this force which is applied over the charge by this component, because of that charge will start moving. Charge will start moving, and this is not possible in electrostatics, because we are talking about electrostatics. Okay, charges are at rest, and this will disturb the entire system, which is not possible. And that's why do remember that the electric field lines will always be perpendicular to the surface of the conductor. Okay, make this thing very clear. Now suppose we have to find the strength of the electric field. Okay, suppose we are talking about the strength of the electric field.
There are only 4 properties.
There are now strength of electric field. As I told you that the strength of electric field is given by electric field intensity. Okay, it is given by electric field intensity, right? So around any charge, suppose there is a source charge, okay, plus Q, and around this charge, if you have to find electric field intensity at this point P, okay, so basically what we do, we draw the electric field lines from this charge. Okay, we'll try to draw the electric field lines as many as we can, because there can be infinite number of electric field lines which can actually come out perpendicular to that surface of the charge. Okay, so like this, these field lines will come. Okay, now what we are doing, suppose that near to this charge point P, if we take a particular area, okay, select a particular area like this. Suppose we selected a particular area, and then what we are doing, we are trying to find the number of electric field lines. Okay, we are trying to find the number of electric field lines, which are actually crossing, which are crossing normally. Normally means perpendicularly, normally to a unit area. Now this area is a unit area, okay, like 1 meter square, 1 centimeter square, like this. So normally to a unit area which is actually drawn near to this point. So suppose this is the point P where you have to find the electrical intensity. So what you have done, you have drawn a unit area near to that, and you are trying to find the number of electric field lines which are crossing normally to unit area drawn near to that point. Okay, now this is too theoretical definition, we should say. Okay, because who will count these number of electric field lines? I don't think that anyone will be able to do that. Correct? How will we count these number of electric field lines? Will it be possible? No. But what we can do is, correct or not? So what we will do is, see, what will happen that if we take a charge, and we'll draw electric field lines around it, so we will be getting actually a solid angle here. Okay, we will be getting a solid angle. You know the concept of solid angle. Okay, steradian is the unit of that. So we will get a solid angle, we call it del omega, a small solid angle del omega we will get. Okay, and if we do one thing, suppose that we take different radii. Okay, if we take different radii, like different distances, r1, r2, r3, r4, different distances we take, and then if we multiply, see, solid angle is defined as, solid angle omega is defined as area upon r square. Okay, this is how it is defined. So area will be omega into r square. Okay, so this is how you can define the area. Okay, this is how you can find the area subtended by that solid angle. Like if we are taking this area, so we will be joining it like this, and whatever the radius is, radius square multiplied by this omega will give you the area subtended. Okay, this is how you can find the area. Now what happens that if we can find the number of electric field lines cutting this area, then that will be a great help. So we can do that also. Suppose for that what we have to do, we have to assume that there are number of electric field lines which are crossing unit area, and by that we can do this. So if we do some mathematics here, so by that we can conclude that the electric field intensity means the number of electric field lines which are crossing unit area, they are actually inversely proportional to the square of the distance. Okay, this is extremely important. Intensity, electric field intensity, that is the strength of the electric field, is inversely proportional to the square of the distance of that point from the charge. So suppose that this point P, if point P is situated at a distance r, okay, if it is situated at a distance small r from E, electric field intensity, so from source charge, sorry, from charge plus Q, then its electric field intensity is given by inversely proportional to r square. Okay, so this is what is established with the help of the concept of solid angle. Okay, the concept of solid angle is involved here, and by that we got the idea about the electric field intensity is following the inverse square law. Now see, we will be talking about electric dipoles. Let's understand what are electric dipoles. Okay, so di means two and poles means poles, and electric means, of course, the electricity is involved in it, so charges are involved. So electric dipoles means what? Electric dipole means what? So suppose that there is a positive charge and there is a negative charge. Okay, equal charges. One is plus Q and another one is minus Q. They are equal and opposite charges. And suppose that these two charges are actually kept at a very short distance. Okay, they are kept at a small distance. Suppose that distance is 2a. You might say that if it is a small distance, why are we taking it 2a? So I will answer that because in future when we will do some calculations, so in that case this 2a will be of great use, and that's why we are doing it. And then here will be the midpoint of this setup, and this is called the center of the dipole. Okay, so this setup is actually called an electric dipole. Two equal and opposite charges, two equal and opposite charges, equal and opposite charges, two equal and opposite charges when they are kept at a short distance away, kept at a short or small distance away, then this setup is said to be electric dipole. Okay, now there are many examples of electric dipole. Okay, as far as the net charge on an electric dipole is concerned, the net charge will be plus Q minus Q, that is 0. Okay, so no net charge is there over the dipole. Okay, now do remember this, If net charge is zero, it doesn't mean that the electric field of a dipole is also zero. No, no. Electric dipole's electric field is very much finite. Okay, finite electric field will be produced by the electric dipole, and that we will be discussing about. Okay, now one example of electric dipole you must have seen and you must have heard about hydrogen molecule H2O. So you know that the lone pair of electrons transfer towards the oxygen, and because of that what happens, oxygen becomes negatively charged, something like that. Okay, so basically what happens, that the center of positive charge, center of positive and negative charge actually shifts a bit in case of a dipole. And because the center shifts a bit in, especially in case of molecules, okay, such molecules are called polar molecules, where the centers of positive and negative charges, they shift. Such molecules are called polar molecules. Okay, and in case of polar molecules, what happens, that you can see that it actually acts as an electric dipole. It acts as an electric dipole. Okay, so this is a natural dipole. Now there are certain molecules, they are like that, positive and negative charges center, they overlap. Okay, they overlap, there is no gap between them. Okay, but when we cap them in the external electric field, then they become a dipole. Okay, so these are basically non-polar molecules. Okay, but the best example is this water molecule, because it is a polar molecule. Okay, positive and negative charges, centers of positive and negative charges, they shift a bit, and because of that we can see that they act as an electric dipole. Having said that, you do remember that electric dipole's dipole length, this is called dipole length, it is a very small quantity. Okay, it is a very short length. So that's why these molecular systems, they actually act as electric dipoles. Okay, now comes the question, and that is, what do you mean, or how do you define the strength of an electric dipole? How can we define the strength of electric dipole? Now, as far as the strength of electric dipole is concerned, okay, strength of electric dipole is given by a quantity called dipole moment. We call it dipole moment. Okay, so strength of electric dipole is given by dipole moment, and it is denoted by P vector. Okay, so suppose that we have a dipole setup. Okay, minus q and plus q charge setup is there. Okay, and these two charges are like this, separated by a dipole length 2a. Okay, so electric dipole moment is given by P vector is equal to q into 2a vector. Needless to say that the this dipole moment is a quantity which is actually a vector quantity. Correct, it's a vector quantity, because obviously the vector sign you can see there. Do remember that the direction of dipole moment conventionally taken from negative to positive charge. Okay, this is conventionally we have taken the direction. So direction of dipole moment, conventionally it is taken from negative to positive. Okay, as far as its magnitude is concerned, we can draw its magnitude, and the magnitude is given by magnitude of P vector is equals to q into magnitude of 2a vector. Okay, so this is the magnitude of electric dipole moment. Okay, and this is how you can actually find the strength of the electric dipole moment, electric dipole. Okay, also as far as unit of this is concerned, do remember that unit of this is given by Coulomb meter. Okay, unit of this is given by Coulomb meter. Unit of charge is Coulomb and unit of distance is meter, so it gives you Coulomb meter. Okay, now do remember that if we are talking about an ideal dipole, so in case of an ideal dipole, this 2a length will be smaller and smaller, tends to 0. Okay, means almost zero. So if we say ideal dipole, so ideal dipole has almost zero size. There is no size at all of the ideal dipole. Okay, this is what they consider an ideal dipole. So this is what dipole moment is. I hope that you are able to follow this. Suppose in this question it is given that there are two charges. Okay, charges 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 plus minus 20 nanocoulomb. Okay, and separated they are separated they are separated by 5 millimeter. Okay, this is the distance by which they are separated. We have to calculate we have to the calculate the we have to calculate the magnitude magnitude calculate the magnitude and magnitude and direction of dipole moment. Magnitude and direction of dipole moment. Okay, so how will we proceed? So what is given? It is given that the charge q is plus minus 20 nanocoulomb. It is given, and distance between them is given 5 millimeter. So this distance will be 2a. Do remember that, because we denote it by 2a, right? And what we have to do, we have to find the dipole moment, strength of the dipole moment, p, magnitude. So p will be q into 2a. Okay, and q is 20. Nano is 10 to the power minus 9 into 2a is 5, so it will be 5 into 10 to the power minus 3. Okay, and you can solve it further. 5 2s are 10. Okay, so that makes it 100 into 10 to the power minus 12. Okay, so this makes it 10 to the power minus 10. Okay, and the unit will be coulomb meter. So this is p. And as far as the direction of this is concerned, you know that conventionally we always say that the direction will be from negative to positive charge. From negative to positive charge will be the direction. Now we will try to find the electric field intensity due to an electric dipole. Electric field intensity due to a dipole, due to an electric dipole or due to a dipole at an axial point. Now what is an axial point? Do remember that when we say an axial point, so see, here we have minus q charge, here we have plus q charge. This is the center O, and at this point, see, if we extended this, so this point P is called an axial point. And what we are going to do, we are going to find out the electric field intensity at this axial point of the electric dipole. Now we have assumed that this x is the distance of this point P, which is situated on the axial point of the electric dipole from center O of the dipole. Okay, now how will we proceed for this? So you know that here we have a minus q charge. Okay, here we have a minus q charge, and this minus q charge will exert a force on this positive, on this charge P. And if we have to find electric field intensity, you know that you have to keep a unit positive charge here at P. What will happen? This minus q charge, it will be attracting this positive charge. Okay, let the force by which it will attract, or let the electric field intensity of it is given by E1. Okay, so this is for the minus q charge. Minus q charge will attract it. After that, if we think about another charge plus q, certainly what will happen, this plus q charge will repel this positive charge which is kept at point P, test charge. kept at point P, and it will repel. So this repulsion will be taking place like this. Okay, do remember I have deliberately drawn these two arrows of unequal lengths. What might be the reason behind it? You know that these two charges are equal in magnitude. Okay, they are equal in magnitude as it is clearly visible. However, you also know that their distances are different. If we talk about the distance of this point A or negative charge from this point P, so this distance is more, correct or not? And if distance is more, you know that electric field intensity would be lesser. Opposite to this is here, this positive charge plus Q is at a shorter distance from point P, and that's why its effect would be more as compared to charge minus Q. And that's why see this E2 vector is of longer length and E1 vector is of shorter length. I hope that this makes sense. Now what we can do is we can write the formulas for the electric field strength. Okay, so at point P, electric field intensity, electric field, as we know that AP is greater than BP. AP is greater than BP means this distance is greater than this distance. So do remember that electric field intensity is actually inversely proportional to the square of the distance. When we are saying AP is greater than BP, then in that case what will happen, that intensity at this point P, because of this minus Q charge, certainly this will be less as compared to the electric field intensity due to this plus Q charge. It means E2 is greater than E1. So do remember that electric field intensity E2 due to this plus Q charge would be more as compared to this minus Q charge. So now at point P, at point P, the electric field intensity, okay, if we have to find, then the resultant electric field intensity will be the resultant of E2 and E1. Now E2 is greater than E1, it is obvious because of the distance, you know. So we can write it is E2 vector minus E1 vector. Okay. Now if we want, we can take the magnitude for the sake of convenience. We can take it as magnitude. Okay. So what we can do is we can simply take the magnitude. Why? Because we know the direction of the resultant. Okay, so what we are doing, we are taking the magnitudes here. Okay, mod means magnitude. Okay, so this is the value of ER vector. Okay, now we have to find E2 and E1. So if we are finding E2 or E1, if we are finding E1, E1 is the electric field intensity due to this negative charge, minus Q charge, because its direction is this side. You know that small positive charge will get attracted towards the negative charge only. So E1 is because of minus Q charge. Okay, do remember that. And the formula for electric field intensity, how do you write the electric field intensity due to a charge at a point? You know, electric field intensity is given by F upon Q naught. And how do you write the force? Suppose that charge is Q, so you write K. K means 1 upon 4 pi epsilon naught Q1 Q2 upon R square. This is how you write, where R is the distance. Also, what you have to do is you have to divide it by Q naught, that is the test charge. So when you divide it by Q naught, it will be cancelled and you will be getting the electric field intensity as KQ upon R square. Okay, so this is the formula for the electric field intensity at a point due to a charge. Now what we have to do here is, you see, E2 minus E1. So first we are writing E1. E1 will be K, and you know what is K? K is nothing but 1 upon 4 pi epsilon naught. In short, we write it K. Okay. K, Q1 means the source charge. So source charge magnitude is Q only, divided by the distance square. What is the distance? Distance will be AP square, because we are finding the electric field intensity E1 due to this minus Q charge. So distance will be AP square. Okay, and this is the magnitude. Okay, similarly you can okay, then in the next step you can write E1 is equal to KQ. What will be this AP? AP will be AB, or you can say AP will be AO plus OP, and AO is what? AO will be A. This complete length is 2A, so this will be A. O is midpoint, so this length will be A. Correct? So you can write A plus X, because we know that this distance from the center to this point is X. So we can write it as, or in some books they write it R. So if you want, you can take R also. So it will be what? R plus A whole square. Okay, this will be the value of E1. Clear? Then we can find E2, and E2 is the electric field intensity due to this positive charge plus Q charge at point P. And for that, what we'll do, again the same thing, K, magnitude of charge is Q only, divided by the distance square, that is BP square. So this will give you BP square, and in the next step you can write E2 is equals to KQ upon BP. BP is what? BP will be, this distance is R and this distance is A. So we can write R minus A. Correct? So we can write R minus A square. So this is how you can find values of E1 and E2. Now what we are going to do, we will be using this equation number 1 and substituting these values of E1 and E2 in this. So let's substitute these values. Okay, so this is the expression and these are the values of E1 and E2. So let's find ER now. In order to do ER, what we'll do, we'll substitute it. You see, KQ is common in both. So we can take KQ common in both. E2 is what? 1 upon R minus A whole square minus 1 upon R plus A whole square. Okay. And then we can take the LCM. This will give R minus A square into R plus A square. Okay. And then R plus A square will go here. So it will be R plus A square minus R minus A square. Now you have to square it. So when you square this, R square plus A square plus twice RA minus, we will multiply minus R square minus A square plus 2RA upon, in denominator now you see, what we can do is we can write it like this. We can write it like this. See, R minus A into R plus A and its whole square will be there. Okay, like this we can write R minus A into R plus A whole square. In very next step, what we can do is we can further solve this. You see this A square, R square, they are cancelled. 2RA will become 4RA. So next step it will be KQ. Okay, 4RA upon R square minus A square whole power 2. Because R minus A, R plus A will be R square minus A square. In very next step, what we can do, we can write ER is equal to K, and what is there? Q into 4RA. So we can write it like this, Q 2Q into 2A, okay, divided by R square minus A square whole square. Okay, because 2 2s are 4 will be there and one R is missing, so that R in numerator we can write it here. Okay, this is how we can write. You can see that 2 2s are 4, 4QRA. This is what was there in the numerator. 4QRA, and that's what we adjusted here. Okay, now you must be wondering that why did we do that? So you see here, P is equals to Q into 2A. We know this. So what we will do, this Q into 2A, what is there, we can write it P, and P is nothing but the electric dipole moment. So in very next step, we can write ER is equal to K 2PR upon R square minus A square whole square. Okay, Now, in this particular case, what we'll do, we will assume that r square is extremely greater than a square. Okay, so if it happens, then we can write r square minus a square equivalent to r square. So next step, we can write er is equal to k 2pr upon r square and its square, because r square minus a square we have written r square. So next it will be er is equals to k 2pr upon r to the power 4, and this will cancel, so it will give you r cube. So this is the expression er is equals to k 2p upon r cube, and this is the expression for electric field intensity at an axial point of the electric dipole. Also, its direction, if we are talking about, so direction will be, see, E2 is greater, so its direction will be in this direction, that is along OP. So we further write here that the direction will be along OP. So this is the expression for electric field intensity due to an electric dipole at an axial point of it. I hope this is clear.